We are next going to look at how we can make inferences about our probability of success parameter pi from a logistic regression model. To help simplify some of our presentation here, we're going to look at simply a model that has one explanatory variable in it. Let's call it x. So our model is a logit of pi is equal to beta zeros plus beta 1 times x. Or equivalently, we could write the model as pi is equal to e to the beta 0 plus beta 1 times x over 1 plus e to the beta 0 plus beta 1 times x. We're going to talk about two different types of confidence intervals. We're going to begin with a walled confidence interval here. Similar to what we've seen before, what we're going to do with these walled intervals is find a confidence interval for a particular quantity and then do a little transformation of that quantity to get it into what we are interested in the end, and that is the pi scale. We're going to get a confidence interval for pi. Okay, so first of all, if we take a look at our model here, we could find a confidence interval for logit pi itself. In other words, find a confidence interval for beta 0 plus beta 1 times x. How would we do that with a walled confidence interval? Well, we would take the corresponding estimate plus or minus the value from the standard normal distribution divided by the square root of the estimated variance of that estimate. Now, to find this particular variance, we need to look at the following result that would typically be seen in a mathematical statistics course. You know, if you haven't seen it before, that's fine, but you do need to know how to apply the result. So let's say I have two random variables, y1 and y2, with constants a and b. So these are numerical values or constants. If I want to find the variance of a times y1 plus b times y2, all I would need to do is take a squared times the variance of y plus b squared times the variance of y2 plus 2 times ab times the covariance of y1, y2. In a mathematical statistics course, you would actually prove that result, but we can apply it here. So in our particular case, I need to find this particular estimated variance. So for us, a is 1, b is x, y1 is beta hat 0, y2 is beta hat 1, and then this is how I can get my estimated variance of beta hat 0 plus beta hat 1 times x. Now, where do I find these individual variances and that covariance? Well, this is where I can go to my estimated covariance matrix to get those corresponding quantities. So now that I have a confidence interval for beta 0 plus beta 1 times x, notice in this alternative formulation of my logistic regression model, look where beta 0 plus beta 1 times x appears. So I can use this same kind of transformation then to find the confidence interval for pi. So with my walled interval before, I put that in my exponential function. Divide by 1 plus the exponential function evaluated at that walled interval before. So in other words, my lower bound of my interval will result from using the minus in both of these places. The upper bound for my interval for pi results from using the plus sign in both of those places. So that's a walled confidence interval for pi if I only have one explanatory variable. When I have more than one, you can see that the equation becomes a little bit more complicated there. In particular, this estimated variance becomes a little bit more of a chore to find. On your own, outside of these notes, I guess you could say, verify to yourself that if p was equal to 1, meaning I had one explanatory variable, verify that this expression for the estimated variance simplifies down to what we would get here. Then take a look at what happens if p equal 2, meaning you have two explanatory variables. What would happen? Okay. So these walled confidence intervals work pretty good in this situation because we have this nice little transformation that we're working with. A better interval, though, to work with is a profile likelihood ratio confidence interval for pi instead. Now, we've seen profile likelihood ratio intervals before for an odds ratio. Now, since I am working with this beta 0 plus beta 1 times x1 plus beta 2 times x2 plus all the way down to the pth explanatory variable, the computational process actually becomes much more complicated. In fact, there can be situations where simply we're going to have to use a numerical or an iterative numerical procedure to do these computations. There will be times where this iterative numerical procedure doesn't work. It doesn't find the confidence interval, or it might give you a confidence interval that actually doesn't make any sense. So please be forewarned that this is actually a much more complicated process. And so be on the lookout, as you will see shortly, of when problems might occur. So to find in R then this corresponding interval, we need to use a package that's written by a user of R called MC Profile. This is a general purpose package that's used with a variety of different models, not just necessarily logistic regression model, to find these profile likelihood ratio intervals. Now, there will be times when you use this that you may see some kind of warning message printed. Oftentimes, these warning messages are not something of concern, but there will be times where it is a concern. And so the problem is, well, how do you know, is this something of concern or not? And one, I guess, rule of thumb to use is that go ahead and calculate that the walled confidence interval. And if you see a profile likelihood ratio interval that's really, really different from the walled, then you should be concerned that maybe that profile likelihood ratio interval is not being computed correctly. Okay, so let's take a look at an example. We're going to go back to the place-kicking data set again. For right now, we're going to focus on a model that only has distance in it. The results from this model fit are stored into an object called mod.fit, as we've seen before. Now, previously, also as what we've seen before, we've seen how to find the estimated probability of success from this model. What I could do is I could go into mod.fit, take out coefficients, which gives me my beta hats. And if I look at the first element, I get beta hat 0. The second element's beta hat 1. And if I want to find then the estimated probability of success for a distance of 20, I could put 20 in there for the distance value. I do those calculations. I'm going to put that in an object called linear.pred. This gives me, now you could say beta hat 0 plus beta hat 1 times 20. Or equivalently, you could say this is giving me my logit of pi hat when distance is 20. Then, using the exponential function, I can find then the corresponding estimated probability of success. I get pi hat. We've seen this code before. There are easier ways to perform this particular calculation. In particular, I'm going to focus on using the predict function. The predict function is a generic function in R because there are many different kinds of models out there where you want to do some kind of prediction with, and so that's why it's called predict. The corresponding method function that's actually doing the calculations for us is going to be called predict.glm. Okay, so let me go ahead over here to tin and do the calculations in there. So first what I'm going to do is I'm going to create a data frame in R that contains my values of distance that I'm interested in predicting at. So I say data.frame distance equal 20. I put that into an object called predict.data. And there we go. So if I just type predict.data, if I can type it, I see I have a data frame with distance of 20. Next, I'm going to use the predict function. I need to specify where my information about my model fits located in the object argument. And then for the new data argument, this tells R, what do I want to predict at? Well, distance of 20. So I go back to my data frame. I specify that right there. And to begin here, I'm going to do a type equal link. And so what you're going to see occurs is I get 3.51. If I come back over here to Word, we've actually seen that value before. That was my beta hat 0 plus beta hat 1 times 20. So the link argument gives me essentially the estimate of the logit of pi, where logit is kind of what's linking pi to the beta 0 plus beta 1 times x into my general model format. Now, to get the estimate for the probability of success, I can change my link type. I can change the type argument from link to response. Our response is our good variable. It's a 1 or a 0. And by saying response there, this gives me then the estimated probability that good is equal to 1. Estimated probability of success. And here's the 0.97 that we saw before as well. Okay. With that as background now, let's look at how we can use the predict function to find our walled confidence interval. First, I'm going to use the predict function to help me find an interval for beta 0 plus beta 1 times x. In other words, for the logit of pi. Here's how it can be done. Okay. So I'm going to say predict object equal mod.fit again, new data equal predict.data. I'm going to work with type equal link because I want to find information to help me get an interval for beta 0 plus beta 1 times x first. And then SE equals true. Standard error equals true. Remember what a standard error is? All it is the square root of the estimated variance of a statistic. In this case, our statistic is beta hat 0 plus beta hat 1 times 20. So I'm going to also set alpha to be 0.05. I put this in an object called linear.pred, and here we go. So linear.pred has a little bit of a different format from what we saw just a few minutes ago. It's actually in a list format, and I would like to be able to type it. So if I say linear.pred $fit, there is my beta hat 0 plus beta hat 1 times 20. If I say instead SE there after the $, I pull that out of that list format and I get 0.17. So this is the square root of the estimated variance of beta hat 0 plus beta hat 1 times 20. Okay, now using that information then, what I could do if I wanted to find, let's say, just pi hat itself, I could. If I want to find now my confidence interval for beta 0 plus beta 1 times x, I take my beta hat 0 plus beta hat 1 times 20. I take it plus the value from my standard normal distribution, and then I take it times the square root of that estimated variance. And so here's my confidence interval then for beta 0 plus beta 1 times x, or in other words, logit of pi. To find the confidence interval for pi itself, I use that transformation that involves the exponential function. And there's my confidence interval. So I'm 95% confident that the probability of success for a place kick at 20 yards is between about 0.96 and 0.98. That would be the standard interpretation. Okay. So we go ahead and find where we are in the notes. Now you could actually find a different walled confidence interval where you take the direct estimate for pi plus or minus a value from the standard normal distribution times the square root of the estimated variance of pi hat itself. I strongly recommend not using this form of a confidence interval for pi. The reason being is because there are no restrictions on if the lower limit could be less than 0 or the upper limit could be greater than 1. Now with our interval, using this transformation that involves the exponential function that we saw, if I can get there, This restricts the values to always be between 0 and 1 for the lower and the upper limit. So that's why I recommend using this version of the walled interval versus the other version of the walled interval. Okay. Now let's say that you want to calculate a walled confidence interval for a different model. A walled confidence interval for pi involving a different model that has change and distance in it. We've seen this model before. We've estimated this model before. We had put the results into an object called mod.fit2 in the past. Also, let's say you're interested not just at a distance of 20, but maybe a distance of 30, where maybe both times you're interested in change equal 1. So these are, let's say, lead change place kicks. Maybe they have more pressure on the place kicker. How can we do these calculations? Well, in R, let me actually go to 10, I can create a new data frame that contains those values of my explanatory variables that I'm interested in. So I have distance, I have change. These names need to be the same as what R recognizes for the variable names in your data frame itself. So whatever in the place kick data frame. I can specify alpha. And then if I use predict in much the same way as before, let's take a look at what happens. Notice what I get. Fit has two components to it. This is for a distance of 20 yards and change equal 1. This is for a distance of 30 yards and change equal 1 as well. So if I wanted to access, let's say, just one component there, like the first one or the second one, I can do it in that manner there. Here's the corresponding estimated square root of the estimated variances for these two scenarios of distance and change. And so what I can do is now find a confidence interval for pi itself. So let's say I'm interested in a distance of 20 yards. First, I find a confidence interval for beta 0 plus beta 1 times 20 plus beta 2, let's say, times the change, the value of change, which would be 1. Actually, yeah. So I grab out that logit of pi hat plus the value from the standard normal times that standard error. So let me go ahead and do that. Here's my confidence interval for the logit of pi. Then I can use my exponential function transformation in the numerator, then also in the denominator. Now here's my confidence interval for pi. So I'm 95% confident that when distance is 20 and change is equal to 1, my probability of success for the population of all place kicks is between 0.94 and about 0.974. Okay, I can do a similar thing for 30 yards as well. Okay, so notice how this confidence interval, our estimate of pi is decreasing because now the place kick is becoming longer in distance. Okay. So let's talk about how to do the profile likelihood ratio interval. This is going to be a little bit more complicated to work with here. I'm going to go back to our model that has only distance in it, and I'm interested in only 20 yards. Similar to what we found with the walled interval, what I'm going to do first is find a profile confidence interval for beta 0 plus beta 1 times 20. Now I could also rewrite this as, let's say, 1 times beta 0 plus 20 times beta 1. So 1 times beta 0, of course, is beta 0. And to use the MC profile package, I need to create a matrix that contains these coefficients of my betas in it. So this is how I can do it. K is going to be my matrix. I could use a different letter if I wanted to, or a different name. Matrix, then the first argument's data. This is where I put my coefficients. I combine them together using the C function. There's going to be 1 row and 2 columns in this matrix. So if I actually then say display K for me, I have 1 and 20. For those of you who've had a matrix algebra class in the past, basically what I'm doing is I'm forming a 1x2 matrix, in other words, a two-dimensional vector. And I'm taking that times a vector of my betas that I have corresponding to my model. That's all I'm doing. If you haven't had matrix algebra, that's okay. Just think of this as we are simply trying to put our coefficients into our object that has a matrix format to it. Okay, so let me go ahead and go over here to 10 to do that directly. So I say library MC profile. Of course, you need to make sure that that's installed first before you actually do the library function. And there's my K. Now, the main function MC profile that does the hard calculations is a function called MC profile. I guess they didn't want to be creative and call it something else. And inside MC profile, we have two arguments here. The first is you have to specify where your model fit's located. It's in mod.fit. Then we have another argument called CM that stands for contrast matrix, or you can think of it as coefficient matrix. This is where simply you specify K. And so what R is going to do is calculate a whole bunch of -2 log lambda functions corresponding to the restrictions that you would have to lambda for this profile confidence interval. And so if I go ahead and do that, it does the calculations. And if I were to actually state then, and I think I do this in my notes. Yep. No, actually I don't do it in my notes. Let me come back over here. And so this does a whole bunch of -2 log lambda calculations. Using this information that's stored in linear.combo, I can use the confident function with it. Remember how confident was a generic function. There's a specific method function in MC profile then that says, okay, let's take all the computations that are done in linear.combo and form a confidence interval with them. So if I say object equal linear.combo, I want a 95% interval and a just equal none. I'll explain why I did that a little bit later on. I put the results into ci.logit.profile. Why do I call it that object? Well, I'm finding a confidence interval for beta 0 plus beta 1 times x, where x is 20. Or in other words, I'm finding a confidence interval for the logit of pi. So let me actually show you what happens. And this is what we get. So this is the logit of pi hat, or beta hat 0 plus beta hat 1 times 20. Then the lower bound for this confidence interval is 3.19. The upper bound is 3.87. Again, a confidence interval for beta 0 plus beta 1 times x, or logit of pi. So there's that confidence interval. Now, the results inside of ci.logit.profile are actually stored in a list format, similar to what we saw when we had the GLM function. It would store the results in a list format as well. So if I want to see what's actually inside there, everything, I can use the names function. And if I say, let's say, notice here's an estimate there, there's a confident there. So if I say ci.logit.profile $confident, notice how I get then the corresponding interval out. The reason why that's important to us is because I don't want a confidence interval for the logit of pi. I want a confidence interval for pi itself. So I can apply my transformation with the exponential function in the numerator and then 1 plus the exponential function in the denominator to the results of what's in confident. That has two elements to it, and R correctly applies then this transformation to both elements simultaneously, so that now my confidence interval for pi itself, 95% confidence interval, is 0.96 to about 0.98. That's how I can use MC profile to do these computations. Let me come back over here. Let me make sure I've talked about all these comments already. I believe I have. Okay. So at least for this particular calculation is not too difficult. The key that sometimes that students, or the key issue that sometimes students have, is that you have to correctly form that K matrix. Again, all K is basically the coefficients that you would put on the betas. That's it. Now, in my actual program, I want you to take a look at some additional examples of how I've used the MC profile package. Let's say you want to calculate an interval for pi at more than one distance. In the end, K, let's say if you have two distances, 20 and 30 yards. Now, K is going to have two rows to it. One for the 20-yard place kick, if that's the first distance, and then one for a 30-yard place kick, if that's the distance that you're interested in. Also, with the MC profile package, you can control the family-wise confidence level. Now, in the prerequisites for this particular course, all of you should have seen a family-wise confidence level before. Typically, it's introduced in the context of analysis of variance and doing multiple comparisons. It essentially has the same meaning here. Real briefly, just to review, let's say I want confidence intervals at 20, 30, and 40 yards for distance. So I want 3 confidence intervals, and maybe for each, I calculate 95% confidence intervals. Okay. Now, the overall confidence level that these intervals contain, each of the 3 different values of pi, is not 95%. It's actually something lower. And so there are ways then that you can control then the overall confidence level for all the intervals that you're interested in. And that's what the family-wise confidence level does. And so in my R program, I show you how you could do that. And basically what it comes down to is that you can, where do I specify that? Actually, I don't have it listed there, but I do in my program itself. Rather than saying adjust equal none, you can use some other term here for the adjustment to control the family-wise confidence level. So for example, if you want to make a Bonferroni adjustment, you can type in the word Bonferroni there in there. If you left this off, it will automatically do an adjustment for you using something that's very similar to Tukey's honest significant difference method that you would typically see in a intro stat course. If you haven't, let me know and I can explain it. Okay. Now there also happens to be a function in in the MC profile package called wald. And so rather than, let's say, using the confint function in MC profile, you could, in the exact same way, you can use the wald function and we'll find the wald confidence intervals. Try it out. See if you can match the results that we've seen before. And lastly, you could also use MC profile to find a confidence interval for the model that has both distance and change in it. The one difference that you're going to see from what we just had for distance is that the K matrix, instead of having 2 columns, now has a 3rd column to take into account change. Okay, the last topic that I want to discuss in this section of notes is how one could use a package called EM_means to do the wald confidence intervals. Now you might be wondering, well, I've kind of said that the wald confidence interval is not quite as good as the profile likelihood ratio interval. So why don't we just always use a profile likelihood ratio interval? No, I told you about there can be problems with the computations with it. Also, because of this transformation that we're making with the wald interval, the exponential function divided by 1 plus the exponential function, that actually helps that wald interval perform fairly well. And so lots of people still end up using the wald interval for that reason. Now the EM_means package is a general, let's say, purpose package that's used with a variety of different statistical models to find confidence intervals for a variety of different aspects of a particular model. When I teach an introductory stat course, I actually show students how to use the EM means package relative to doing multiple comparisons with ANOVA models. So some of you, depending upon what intro stat course you've had in the past, probably have seen the EM means package before. And so I want to take a little bit of time talking about how to use the package in this context. Now, in the end, would I use the EM means package to do the wall confidence intervals here? Well, no, there really isn't an advantage to it. But as you will see later on in the book, in the course, for more complicated settings, the EM means package can be helpful. It can make some computations more easy. Just note that, as I like to put, there are some quirks to using this particular package. Okay, with that as a little bit of an intro, let's talk about how we can do these computations in ARM. Okay, so this is a package that was originally written by Russ Lenth, who was a professor at the Department of Statistics and Actuarial Science at University of Iowa. It is on CRAN, Comprehensive R Archive Network, so you're going to need to download it to install it. And then once you do that, say library EM means, and now you're ready to go. Now, similar to what we did before, we need to specify, the values of, let's say, x. If I'm just working with, let's say, with the model that has just distance in it, I need to specify the values of distance that I'm interested in making these predictions at, what I want the pi hat for. And so to do that, I could use data.frame, just like what we did before, to create a data frame that contains that in there. Instead, I'm going to use a more general format, and you'll see why I do this and why EM means expects you to do this shortly. And I'm going to use a list function, list distance equal 20. Remember how a data frame is a special case of a list? So that kind of gives you some connection of why this is done. So I'm going to say predict.data2 gets a list that has distance equal 20 in it. And then the main function that does the calculations for us is called EM means, where I specify, similar to what we saw with the predict function, object equal mod.fit, where I've stored my results. Specs means your specifications. I want to do these predictions at a particular distance. And what we see here is kind of like a formula, like syntax, like what we saw for GLM. It's not exactly, but it is kind of like that. You can think of it that way for now. Where do I want to make these predictions at? Well, I use the at argument, and this is where I specify my predict.data2. Type of predictions, I want to predict the response. What this translates into is I want to come up with pi hats, and then I can specify my confidence level, let's say 95%. So if I go ahead and run this, this is what I get. This again is a walled confidence interval. The asymph.lcl stands for lower confidence limit. Asymp corresponds to asymptotic. We've seen that term used before relative to walled confidence intervals. So that's where the terminology comes from. You see DF for degrees of freedom. That just simply means that we're using a standard normal approximation. And hopefully in an intro stat course, you'll learn that if you had a t distribution with an infinite number of degrees of freedom, that's equivalent to a standard normal distribution. We see some other calculations here as well. And what we end up with is exactly the same walled confidence interval that we had before with the predict function. It does the correct transformation that we need. And that's what all this text here means. Back transform from the logit scale. So it finds a confidence interval for the logit of pi first, or beta 0 plus beta 1 times 20 first. And then it uses that transformation to find a confidence interval for pi itself. Okay, let me come back over here to Word. So it's fairly easy to use in this particular situation. Let's see here. If you have more than one explanatory variable, you could include them in the specs argument as well, or you would need to, where you would say, like, let's say, for example, distance plus change. Let's see. Now, the main thing that I want to get at in terms of a quirk is this at argument. Now, the at argument kind of plays the same role as the new data argument that we saw in the predict function. The difference is that we need to specify at specifically as a list. Here's why. Consider the situation where I had distance and change both in my model. I need to specify all the values of distance and all the values of change that I want to find the corresponding pi hat at that we saw before. The way that the at argument works is that with at, when you specify a list, you specify the distances and you specify the unique values of distance that you're interested in and the unique values of change that you're interested in. So notice the difference here for change. Since I was repeating change, I don't need to do that here. What means will do is say, okay, I'm going to match up change with 20. I'm going to match up change with 30 and come up with two different predictions or two different pi hats corresponding to this. That's just unfortunately the way that this particular function is set up, and so you need to take that into account when you use it. One last thing here that I do want to mention is that, and it's in my notes earlier, but I think I failed to mention it during this recording, is that in the new data argument in the predict function, the way that I introduced it was I put a data frame predict.data in there where I created this data frame outside the predict function. You don't have to do that. You can simply put the data, you can automatically create the data frame right inside the function itself. Now, obviously, if you had a lot of different values of distance, a lot of different values of change, or if you had other explanatory variables, it makes some sense to do it outside the predict function. But when you only have a few values as we do here, you can do it right inside the predict function. In a similar manner, for the at argument for means, you can create that list right inside of it if you wanted to. Okay, and just for emphasis, the means doesn't provide much of a benefit for this particular situation that we're looking at. I'd be fine with just using predict like what we did before. However, I purposely introduce it in a simple setting such as this so that when we get to more complicated settings, we can take our knowledge from here to that more complicated setting. It will be easier to use. Okay, so this concludes in this part of doing inferences for our probability success parameter from a logistic regression model.